Okay, so for this video, we are going to do an example problem for buoyancy. And here we have a cube. Is it a cube? It is a cube, 1 meter by 1 meter by 1 meter, submerged to a height of 0.2 meters, 25 meters, sorry. And we want to know how far the spring is stretching to hold it in place. There's a spring here with a spring constant of 10,000 newtons per meter. We're going to assume that this box has no mass since the mass is not given and that it's completely hollow. So which model will we use? All right, which model will we use? First of all, whenever we ask ourselves this, we have to ask ourselves, what are we trying to do here, right? If you're saying, well, I'm trying to figure out a force, then the first thing you should do is not the most specific model, but the most general model, right? So in that case, our most general model is the model of mechanical engineers, which is, and aerospace engineers, if we're being honest with ourselves. It's just not the model like electrical engineers. Some of the forces is equal to mass times acceleration. In fact, actually, civil engineers also use this model, but they always they always have this equal to 0. So I don't know what that says about civil engineers, but great. So some of the forces equal to mass times acceleration. We also have a couple other models that we think we might use, so let's just write them down right away. We have a spring in here. So let's not use that. Let's not use that color. We have a spring in here. So we're going to say that the force due to a spring, F spring, is equal to K times X, where X is the distance the spring is stretched. And the last model that we have is our buoyant force. F buoyant is equal to rho G V submerged, right? Great. Great. So, just a reminder that the second we write down F is equal to MA, we know that we have to write a free body diagram down. If you do not put a free body diagram down on an exam or on your homework, you will get points off, right? Because it's such an important part. So much information is conveyed, not just to graders, but to people who are working on a problem with you when you write down a free body diagram. All of your assumptions are laid bare, essentially. And that's why it's so useful. It's easy to catch your mistakes when you write a free body diagram, so do it. All right, let's also, now that we're bringing up our coworkers, future coworkers that we haven't met yet, let's write down our assumptions. Assume fluid at rest and rho is equal to a constant. And what else? That should be all we need. Great. So let's start. Let's do a free body diagram of our... Let's do a free body diagram of our box. So let's write that up here. Free body diagram of our box. Let's draw our box briefly. Whoop, whoop. Remember, we always need a coordinate system. X, Y. So we're going to do Y in that direction. Then acting on our box, do we have any weight? Nope, we have no weight. So we do not have a mg, but we do have a buoyant force, FB, and we have a F spring acting down. So if we were to now take equation 1 and tell our graders that we are, and our future coworkers, that we are going to convert equation 1 to equation 2, and we're going to say that sum of our forces in the y direction is equal to our two forces added together. So we have a positive FB minus an FS. And let's take equation 2, add in equation 3 and equation 4, and make that equation, whoops, I mislabeled things here. 1, 2, 3, this should be equation 4. And this is 2, 3, this is equation 2, 3, and 4. Yep, to equation 5 gives us this is equal to 0. 0 is equal to buoyant force, which we can plug this in, which is rho g v submerged, minus our spring force, because that's in the negative direction, which is equal to minus kx. And so we can plug in our numbers here. 0 is equal to 1,000 kilograms per meter cubed times 9.8 meters per second times our volume submerged, which is 1 meter times 1 meter times 0.25 meters, minus our spring constant, which is 10,000 newtons per meter. Newtons per meter times x. And so we check. We always check. How many unknowns do we have? Only one unknown. Great. So we can solve for that unknown, and we find out that x is equal to 0.25 meters. Great. So two things right now. Your engineering sense should be going, wait, 0.25 meters. That means our buoyant force is 2,500 newtons, which is a lot. That's 250 kilograms of the equivalent weight of 250 kilograms, or what, over 500 pounds? That's a lot of weight for what seems like a small amount of submerged water, right? A meter by 0.25 meters. And the answer is yes. Water's heavy, right? Water's very heavy, so buoyant forces can be quite high. Great. Quick note about these numbers. As you just noticed, because of the mistake I made, they can become a little cumbersome at times, a little annoying. But they are very important, right? I've graded a tremendous number of exams in my life, and about half of them are very difficult to follow. And it's fine. You can be a messy writer, right? But what's very difficult is when equations are scattered all over the page, and some of those people think that if they write down enough equations, that they'll get enough partial credit, and they can get enough partial credit to pass, basically. But that's not how I grade, and that's not how we have our TAs grade. Our TAs grade to see if you have a workflow that makes sense. And what they do is they take off points for mistakes, not give points for having correct things on the page, right? So what they'll do is they'll follow what you did, and if you made one mistake in the middle here, like let's say you did a positive instead of a negative, they'll take off a point for that instead of taking off points for everything else, everything for having a wrong answer. Let's fix that so that somebody looks at this later, they don't get confused. But in order to follow your work, in order to see how much you got right, they have to be able to see your thought process. And so if you're the type of person who doesn't think or write down stuff linearly, right? So you don't write stuff one line, second line, third line, fourth line. You have to do this. You have to give us some kind of clue as to what comes after what, right? So that's one reason. And the second reason is that you should know that everybody is human, right? People who read your work at school are human. The graders are human. I'm human. Your coworkers are human. And as much as we would like it to be true that people just judge us based on the final result of our work, it's not true. People judge you based on the how easy it is for them to understand it. And the easier it is for them to understand it, the better they feel about it. And the better they feel about it, the more likely they are to positively rate whatever it is you do. So if you are a contractor, let's say, like you work for a company that contracts for other people, you want your potential solution to be as easy to understand for your clients as possible. And that's almost more important than whether or not it is the absolute correct solution to their problem that you're trying to sell them. Because if they understand it and they are happy, they're more likely to contract you and give you the money you need to buy food, right? And housing. You don't have to buy a house. In fact, sometimes I wouldn't recommend it. So the readability of your work matters, right? If you hopefully you know this term, but everything you write is rhetorical, even the work you do to solve problems, because the work you're doing to solve problems is an argument, and that argument is, I know what I'm doing. Great. Okay, so here's the point where I'd ask if you have any questions, but there's nobody in front of me, so we're just going to move on. Let's talk a little bit about our semester-long design problem. If our tower weighs W kilograms per meter, we don't know how heavy our tower is going to be. How much empty float volume is required for the tower to float? So some context here. This giant tower of awesome that's just going to be spewing, you don't know this yet, but I'm going to tease it a little bit, supersonic sprays of water is going to start floating, right? Because it can't just start sticking up, because how are you going to support it? So it has to start floating on Lake Erie. Let's call this Lake Erie. Lake Erie. It's starting floating on Lake Erie, and then it's gonna be just majestic as fuck. So it's gonna, oh shit. Well, anyway, it's there. It's gonna be so majestic because it's gonna start, and then you're just gonna start rising up slowly, right into the sky until it's pointing almost straight up, carrying whatever load it is we want to be on top. And I'm gonna suggest that the first load is just me sitting here in a little spacesuit. So, but if it's sitting there on Lake Erie, one of the questions we have to ask ourselves is, if our tower weighs W kilograms per meter, and we don't know how tall our tower is going to be yet, because we don't know how tall we can make it, how much empty float volume is required for the tower to float per, I should have added this in, per meter. Okay? And this is an important question because just like with spacecraft, right? Spacecraft, you try to make them as light as possible so that you are not wasting any mass, because any mass you try to get into orbit requires an X amount of fuel, right? The same is going to be true of our tower, just not quite the same argument. Instead of worrying about fuel, we have an almost unlimited amount of water in Lake Erie. We still have a certain amount of flow rate that we have to maintain. And power requirements, but we still want to minimize the weight of our tower, right? So we can't just put giant floats on this, because giant void volumes still require some mass to create. And also, if we have medium winds on Lake Erie, all of those floats are going to cause drag, and so we still want to minimize the amount of float volume required to keep this thing floating. So we're asking about, we're not saying it out loud, but we're asking, what is the buoyant force required to keep this up, right? So, but we are asking for the forces on an object. So one of the first things you should do is you should say, well, we're going to need some of the forces is equal to mass times acceleration. The basic model of mechanical engineering. By the way, is this an accurate model? Yeah, for a lot of what we do. It's not an accurate model, for example, if we are modeling long-term trajectories in orbit, where you might need relativity, or if you're going very, very fast, right? So, but for a lot of what we do, it is. Great, so we have that model, and we also know we're probably going to need our buoyant force is equal to rho g times our submerged volume. Great. So let's write this out. Equation 1 to equation 3. We get some of our forces. And let's do a free body diagram over here. Free body diagram of our object. Anytime we have a free body diagram, we have to do directions just so people know what we're doing, X and Y. And let's draw our forces on it. We have some kind of force, which is going to be our weight, our W, kilograms per meter, times our length. And we know that we're going to have some buoyant force, FB, which is equal to rho G times And we're going to break this up a little bit. We're going to call it A times L, where A is the cross-sectional area. And L is the length. Great. So now we're going to do sum of all of our forces in the y direction is equal to 0 is equal to, because nothing's moving, is equal to our weight times our length, but that's a negative because it's going down, plus our positive rho g times our A times our L, our length. Great. So now we're going to take 3 into 4, and we're going to note that we can cross out our L's, and what we find out is that our and then we can bring our W over to the other side and divide by our rho and G. We're going to do that, and we're going to find out that our W over rho G, where rho is of the water, is equal to our cross-sectional area. So if we wanted to include a void space on a per meter basis, we need to have it be equal to the weight of the object divided by the density of water times gravity. And that tells us, at least per meter, how much cross-sectional area we need to be empty. So if we were extruding long tubes, we could add an empty extruded section in there if we wanted to, which might actually add some rigidity to the structure, which would be useful. Now in real life, right, this cross-sectional area will have its own weight penalty, and you'll have to model that. And it becomes an optimization problem about how you create that void volume, right? Because not only do you want to create that volume in a way that weighs as little as possible, but like we said, we can add rigidity with that if we want to. We can also use that void volume to do things like run power cables or control cables, or use it for some other purpose, right? At which point this becomes a very interesting optimization problem. How much weight penalty are you willing to take while maintaining your buoyant force and also accomplishing these other goals like rigidity and strength that we will talk about later. Cool. Great. So the next video we're going to do is going to be our quiz, not quiz. Like I said, I recommend you either wait to do it until we're doing it in class or do it with a group of people, because these are good problems to discuss and argue about and spend a lot of time on.